Good evening, everyone. Tonight, I am going to be testing OpenAI Deep Research, as well as Gemini Deep Research, yet again on the topic of my PhD dissertation. Now, I wasn't too happy with the way I handled the last testing. I don't think I was as rigorous as I could be, and that was partially because I didn't want to get into the weeds and the nitty-gritty details of my work that I did for my PhD, because it is kind of technical. But this will be that kind of video. I will be getting into the weeds of things. I am going to be explaining things. I won't try to overwhelm. I will do my best to explain every point that I'm making. But in order to really give you guys a feel of, do I think this deep research tool is beneficial, I wanted to come up with a fairly, I don't know if rigorous is the right word, but a pretty serious test, in the sense that I wanted it to specifically not try and do a summary of the entire field, but a summary of the specific 2 papers that I wrote in graduate school. And so these are my first author papers, so I have a very good sense of what is in them and how I thought about them and where I think I could have done better. And so that is what I'm going to prompt both OpenAI Deep Research and Gemini Deep Research with. So the prompt that I'm going to use is write a 1,500 to 2,000 word report on the following 2 papers about dynamical mass measurements of supermassive black holes with the Atacama Large Millimeter/Submillimeter Array, also known as ALMA, and the Hubble Space Telescope, also abbreviated as HST. In your report, be sure to address the following questions and points. What is the main objective or hypothesis of these research articles? What is the significance of carrying out these measurements? What were the observational properties of the telescope data collected? Describe the author's methods of measuring black hole masses. What are the major sources of uncertainty in the error budget of these measurements? What were the values of the measured black hole masses? And finally, what are some areas that the authors could improve on for future measurements? So these are just 7 brief questions that I thought of and think are fair game to ask of these models. And I really want to see them specifically read my papers, so I'm giving them the link to my papers on Archive, because Archive is a preprint server, so there is no paywall or anything like that. The Astrophysical Journal is where they're published, and even though they're open access, it does seem to me that sometimes deep research doesn't recognize that it's an open access journal, in the sense that it can download a PDF and it can read the whole article for free. I have seen it before where it has tried to tell me, oh, I can't access this article, it's not open access, it's behind a paywall, when in fact the journal is completely open access. So I'm giving it Archive because Archive is free and completely open. And so I'm going to go ahead and just copy this prompt, and I already had it there, but I'll just recopy it again into both Gemini and O3 Mini. So I'm just going to hit send on both of them. Okay, so we have OpenAI's Deep Research asking us a few questions. It says here, I can certainly draft a detailed report based on these 2 papers. Before proceeding, could you confirm if you'd like a structured academic style report with sections such as introduction, methods, results, discussion, and conclusion? Additionally, do you have any specific formatting requirements, e.g. citation style, font spacing? I don't really have formatting requirements. I will say, feel free to write it in a way like an academic style report with an introduction, methods, results, discussion, and conclusion section. Write it so that your output can be copied and pasted into a Microsoft Word document without any formatting issues. Other than that, you are free to write as you please. Okay, so, and I think what I might also do is I might give those same sort of instructions with the Gemini model as well. So we'll make sure they have pretty much the same exact prompts, and we'll let it go. So here we go. They're both going to go off now, and now we wait. Okay, so now Gemini is saying a few things here, following sections, and okay. It even made some additions to those sections here in terms of what I wanted. So yeah, that looks good. So we're gonna hit start research. So started the deep research on Google a little bit later, but I don't think it matters too much. I just really want to see how well they're both doing here. You can take a look at what is going up here. So it says here, working through the potentially restrictive DOI link. Really restrictive? Considering archive. I did give you archive. Wait a minute. What's going on here? Rolling. Abstract is fully drafted. Piecing together black hole mass measurements here, but the focus on gas dynamical modeling and stellar mass distribution. Okay, learning about black hole masses, NGs 4076 and 5193 using ALMA. Okay, oh, whoa. Gemini just really took off here. What papers did it go for? Oh, guided. What is this? Is it like learning how to write an article? Seems like it's like trying to teach itself how to write an article here. That's kind of amusing. Well, that's kind of cool. Gemini is like trying to learn on the fly how to do this, whereas O3 Mini, or I should say Deep Research, says here, I'm considering the archive HTML to search for relevant sections, combining key sections. Okay. I'm considering the use of the F160 wide filter, which is near infrared, to minimize dust impact, and possibly adding F814 wide for optical measurements. That F160 wide was a filter that I used images from, for sure. Oh, they're reading my website. What do you know? I'm examining Kyle Cabasaris' publications to link them to a ResearchGate or other site for more details. Trying kylecabasaris.com publications as a possible source. Okay, so that's amusing. It found my website. What did Gemini do? Gemini actually finished here. So awesome. So Gemini is done. I'm going to go ahead and open it in the docs and just take a look at it. O3 is still going, or Deep Research is still going. And let's see here. Okay, this looks like a pretty long report here. And I'm going to go ahead and read it. I know it might be kind of dull and boring, but I'm going to give my commentary about it because I want to be as comprehensive as I can be and give you guys a real good sense as to whether or not this is a good report or not objectively. And we're not going to think too much about formatting and anything like that. I just want to know, is the content good? First off, the title, Dynamical Mass Measurements of Supermassive Black Holes with ALMA and HST, a Comparative Report. Intro. Supermassive black holes reside in the centers of massive galaxies and are fundamental to galaxy evolution. These objects, with masses millions to billions of times that of our sun, exert a strong gravitational influence on their surroundings, shaping the dynamics of stars and gas within their host galaxies. Understanding the formation and growth of SMBHs is essential for unraveling the complex interplay between black holes and their host galaxies. This is a fine intro paragraph, that's all correct. One of the fundamental properties of SMBHs is their mass, which can be determined through various techniques. Dynamical mass measurements, which rely on observing the motions of stars and gas orbiting the black hole, provide a robust and reliable method for determining SMBH masses. The outcome of large millimeter submillimeter array ALMA and the Hubble Space Telescope HST have revolutionized our ability to probe the dynamics of gas and stars in galactic nuclei, enabling precise dynamical mass measurements of SMBHs. Okay, initial summarization of the research papers was conducted using the solar to gain a preliminary list of the key findings of what? Okay, so this is kind of like a what? I mean, I didn't need to know that. That's a little bit of like a what's that? TMI, too much information. This report focuses on two recent research articles that utilize ALMA and HST observations to measure the masses of SMBHs in different galaxies. The first paper, measurement of the black hole mass NGC 1332 from this is already wrong because this is actually my advisor's paper, not mine, even though I asked it specifically to look at my paper, even though I gave it the links. So all right then, we can already say that Deep Research from Google failed because it just did not write about the actual targets that I was looking for here. And so let's just say here, so they looked at 1332. I know that paper really well. I mean, actually there's two of those papers, but yeah, so my advisor wrote this paper and it was not the paper I gave it. Okay. The second paper, Dynamical Measurement of the Black Hole Mass in the Lenticular Galaxy NGC 3998, focuses on the SMBH in the Lenticular Galaxy NGC 3998. No kidding. Okay, so it did not do what I wanted at all. This is a complete fail. And I even gave the links. I mean, I found that amazing that I was able to give it the links and it did not figure it out. This is completely wrong, and it's also not a tilted ring model for NGC 1332. It's a flat disk model. So I know this, we're getting really into the weeds here, but this is actually wrong as well because I know this paper. So okay, wow, what a fail. What a fail by Google Deep Research. Time to see how OpenAI's model did. Let's read it from here. So it did in 8 minutes. It looked at 24 different sources here. This is correct. Correct. And did it cite my paper here? Oh yes, this is mine, and this is mine. So it cites mine again. Okay, so how many times does it keep citing me? That's the same paper 3 times. Okay. Seems like it's unnecessarily citing a lot. Okay, until recently. This is true. This is true. This is pretty good. Yes, indeed. Is this still my paper? It's still citing the same paper over and over again. That's kind of funny. I mean, I did tell it to cite this paper, but it doesn't need to keep citing it on every line. Okay, the 2 research papers under analysis exploit ALMA and HSC together to measure SMBH masses in 4 early type galaxies. This is correct. The first study, mine, targets the galaxies 1380 and 6861. The second, also mine, focuses on 4786 and 5193. Good. It actually got the right papers. So that's already a huge improvement over Google's version. So they're all elliptical or lenticular, contain a circumnuclear dust disk and gas disks, or molecular gas dynamical modeling. This is correct. I'm not going to try and read every single word here. And so far, so good. This is all good here. In summary, this analysis will examine the 2 studies' goals, methods, research results, and implications. The introduction has outlined the motivation for using ALMA HST to measure SMBH masses and why these measurements matter. Next, the method section will describe the observational data obtained and the modeling techniques applied. Okay, so methods. So we use CO2 to 1. That's correct. The first study used cycle 2 data. That's correct. Cycle 3 and beyond. That's also correct. It was cycle 3 and cycle 5. Highly inclined. On the order of 0.3 arc seconds. That is correct. And I'm going to be saying that's a correct a lot, I'm thinking, because all these numbers are accurate. For the starlight distribution, the studies utilized Hubble to map the stellar luminosity and dust in the galaxy cores. Used optical HST to identify a smooth round dust disk in each galaxy, which was a criterion for selecting these targets. That's a good point. That's true. That's how we selected them. And use F110 and F160 wide. The light is less affected by dust extinction, allowing a clear view of the central stellar distribution. Correct. That's exactly why we use them. Also generate point spread functions with tiny Tim. So far, so good. This is all correct. One model might assume no extinction, which could underestimate the true stellar light in dust obscure regions, while another one might attempt an extinction correction or exclude the dusty central region dust mass model. 2024 study, they mentioned producing 3 MGE models per galaxy, likely spanning a range of plausible inner brightness profiles from more shallow to steep to capture the uncertainty due to dust. That's exactly what we did. That was like a huge portion of my dissertation. What do you know? So now we get down to the modeling here. It says here, gravitational potential in galaxies come from 2 components, the extended distribution of the stars and any gas mass, which was found to be a negligible contribution. That's a good point. That is a very, very good catch there. Yes, we did include that, and it is very negligible. I'm glad it pointed that out. And a potential point mass at the center representing the black hole. Okay, thin disk model, correct, constrained by the imaging. We'll try and go quickly here. It says here the model then produces a synthetic data cube, or at least a velocity field. Wait a minute. The model then produces a synthetic data cube, or at least a velocity field and line pose that can be directly compared to the ALMA observations. I mean, it is a synthetic data cube. I don't know why I put this line here. I mean, getting really nitpicky at this point, to be honest. Key aspect of the method is that the authors fit the models directly to the ALMA data cubes rather than just to derived rotation curve. They take into account the detailed 3D info. So that's interesting that it says here that it likely involved. It like sounds like it didn't read the whole thing, which maybe I'm expecting too much for it, but it says these things as if it didn't actually read the paper. It says it likely involved, because if you read the paper, you would know that yes, the black hole mass and all the other parameters were fit using a gradient descent algorithm. So we used CASA, we used LMFit. Also mentioned using codes like this. True, and here we go, uncertainty analysis. That's the big portion. Measuring MBH comes with several sources of uncertainty, which the authors explored carefully. Each fit yields a statistical uncertainty. How well constrained the parameter is by the data given the noise. There are systematic uncertainties from modeling assumptions. Okay, yes, the big thing is the dust extinction. Yes, okay, so they talk about that. That's a good thing here. It says here that 6861, unique source of uncertainty is the absence of CO emission in the very center. That's correct. Very correct. That was a very, very notable galaxy because of that thing. 1380, 147 million, correct. 40% uncertainty, correct. This is the right range. It says here, in other words, a supermassive black hole is required to reduce the observations, but the exact value in that range is certain. 4786, they get that value correct. Then NGC 5193, and that is also correct. Major sources of uncertainty, that's correct. That's correct. And yeah, other systematics as well. Distance, that's good too. Okay, so let's see here. I want to know what it has to say about how we could have done better. So far, it has been very, very good. And this sentence also makes me kind of happy because this is a somewhat underappreciated point in SMBH measurements. So this is actually nice. Hooray. They are acknowledging my contribution by being such a stickler to details. And let's see, areas for improvement. Here we go. So higher ALMA resolution and sensitivity. That's something we could definitely do. And we observed them in a two-stage process. So if we found quality measurements or we found quality targets at lower resolution, we could always re-observe at higher. Multi-wavelength imaging and dust mapping. We always have been talking about multi-wavelength for many years and just never gone around to it. But it is a good idea. JWST is also a good idea. So I think that's good here. Cross-verification is always good. Extended sample and selection criteria. Let's see here, but what do they say here? In future surveys, perhaps an ALMA snapshot survey, many candidate decilanes could identify more targets where this technique can be applied. One improvement is target galaxies where the sphere influence is likely to be resolved. I mean, that was kind of the requirement before, but okay. Alternatively, focusing on somewhat lower mass pHs but very nearby might yield resolved SOIs with ALMA. I think we've already kind of gone through that. Analytical and software improvements. Okay, let's see here. Serial warp and spiral disturbance. That's good. Full Bayesian fittings, also good. Thought about that as well. These are all very good suggestions, though I think some of them are a bit redundant and have already been tried, but there's no way that it could have known. Because in their conclusion, I remark that there are highly important limiting factors and considerations for future gas dynamical measurements. In summary, the main lessons are get the highest resolution in SN possible, thoroughly account for dust and stellar mass profile uncertainty, and always test the extremes to understand the data's requirements. Thank you. I agree. So let's take a look here. I think this is a really good review. It's much better than the one that it produced for like the entire field that I asked for a few days ago, though there are still there's just some wording things and just oversighting things that I'm like, okay, that's a little bit annoying that I don't think a human would do, but the content is good. Let's just start there. The content is really good. I think that it's getting everything I did correct. It's getting all the facts right. It's not conflating the wrong papers with each other. It is focusing on these papers. So perhaps just telling it to focus on fewer things is just better, which is perhaps obvious, but it's cool to see the improvement in quality in its response compared to the last request I gave it when I asked it to summarize the literature of the entire field. So as the author of these two papers, I can say by reading all these things, it sounds like someone really did read my work. Like if someone was talking to me and was talking like this, just imagine this is voice, not text, and we were having a conversation about the papers I wrote, I would think, wow, they really spent a lot of time reading my papers. They must have really gone over it with pen and circled things and wrote stuff down and really thought about the material. So this is really, really, really good. So I hope that gives you a better sense of the capabilities of deep research. using this very, very niche case of me being an expert in this one area of astronomy and having it validate and review papers that I wrote. So that is basically it for the video. I hope you found it okay, even though it was very long. I apologize. I just wanted to be as thorough as possible. I sometimes have a hard time deciding how thorough versus not thorough I want to be with these videos. And I know that talking with all the jargon can get dull over time. But I do think that for this video in specific, it was important for me to be able to read as much as I can and critically evaluate the outputs and give you guys my honest opinion. Also, I do see here dark hearts. I didn't see that before. That's a little bit too prosy for me. If this was supposed to be like a serious paper, I would not want to see dark hearts in a paper. So I just caught that. But again, we're nitpicking here, very much nitpicking. Content really good, and Google Gemini deep research didn't even do it right. It didn't even use the papers I gave it. So anyways, that's all for the video. Thanks so much for watching, and I will see you with future tests.